Well, what we see are 7 jets coming out of these objects, more than 7 actually, after it passed close to the sun on October 29th. And we can see that some of these jets are pointed towards the sun, and they penetrate over 1 million kilometers through the solar wind. We know the properties, the density and speed of the solar wind, so we can figure out that for a natural comet, with the characteristic outflow speed of these jets that come off pockets of ice on a natural comet, given that speed, we can tell that there is a lot of mass carried by these jets so that they can penetrate through the solar wind.
And indeed, the trajectory is aligned with the plane of the planets around the sun to within 5 degrees. The chance for that at random is 1 in 500, okay? And it's moving in a retrograde trajectory opposite to the motion of the planets, which is ideal for it to release mini probes that will get into the planets. It gets close to Mars, it gets close to Jupiter, it goes on the opposite side of the sun relative to Earth when it's closest to the sun. And that's the time when a spacecraft could do a maneuver to take advantage of the sun's gravitational assist.
In astronomy, the simplest measurements often hold the most power. One of the most foundational is thermal mapping, how an object absorbs, distributes, and releases heat as it travels through space. Comets, asteroids, even distant exoplanets all follow predictable thermodynamic rules. They absorb solar energy, store it within their surfaces or subsurfaces, and radiate it outward, typically in chaotic asymmetric patterns. But with 3i Atlas, the new JWST dataset didn't show chaos. It showed a repeating structure. Temperature readings formed concentric bands, warming and cooling in a synchronized loop. This is not noise, it's not a glitch, and it's not a known geological feature. As researchers dug into the data, the pattern became clearer. The heat was moving across the surface in arcs, not random lines, not jagged patches, but smooth, flowing curves that advanced in timing with the object's rotation. It appeared coordinated. Simulations failed to replicate it under any known comet model, changing the albedo, adjusting core composition, accounting for outgassing pressures. Nothing fit. Because there was no venting, no dust, no natural ejection, just a quiet pulse of thermal energy that moved like an echo through the object's shell. The only models that partially reproduced this result required internal structures, channels that distributed heat from one section to another. That's when the conversation changed, because heat doesn't organize itself, not like this. It needs pathways, materials, geometry, which means either Atlas is made of something we don't understand, or it was designed. For the first time, the data forced scientists to place an idea on the table that had always remained hidden in the drawer. If the thermal system behaves like a radiator, then what is it radiating for? As the thermal data was rendered into 3D reconstructions, another unexpected pattern emerged, this time from within. JWST's deep infrared mapping revealed not just heat shifts on the surface, but repeating signals emanating from inside the object. The readings outlined a lattice, an internal grid-like distribution of thermal resonance that appeared staggered, layered, and aligned. What made this so unusual was not just the shape of the grid, but its uniformity. Natural fragmentation of comet interiors typically produces chaotic cavities, voids caused by ice loss or collisions. But this was different. The grid nodes, each a point of thermal concentration, were spaced evenly, connected by what appeared to be faint thermal bridges, and they responded in sequence. A slight increase in one node would be followed by a delayed rise in another, as if heat was being transferred purposefully from one zone to the next. No one wanted to say the word. But the pattern bore resemblance to heat management frameworks found in engineered systems. Speculation began quietly. Could this be a form of internal reinforcement? Or were these thermal bridges not structural but functional, perhaps distributing energy across compartments? To test the idea, researchers ran decay simulations. In a purely natural object, any interior grid of this sort would dissolve over time from impacts or outgassing. Yet the Atlas data showed no such degradation. If anything, the pattern had become more pronounced as it moved through denser solar radiation. One theory suggested a self-regulating thermal mechanism, like radiative fins used in spacecraft to avoid overheating. Another posited crystallized metallic inclusions that absorb and re-emit heat in regular phases. Either way, the conclusion was unavoidable. This wasn't the messy, random void typical of frozen comets. This was a framework, and frameworks imply intention. Over an 18-day observation window, 3i Atlas displayed 8 abrupt brightness increases, not gradual, not solar-driven, sharp pulses, each arriving within a few degrees of the object's axial rotation. That alone was strange. But when the team overlaid the pulse events onto a rotational map, something alarming appeared. Each pulse aligned with the same geometric quadrant, and each was followed by a decay period with near-identical timing. Natural objects don't behave this way. Comets flare irregularly. Their brightness is chaotic, caused by surface eruptions, ice fractures, or random heating. But 3i Atlas pulses like a rhythm. More than that, each brightness event occurs without corresponding gas or dust release. No jets, no visible material movement, just light. Photometric analysis showed a strong spike in the visible green spectrum, followed by a fall-off in the near-infrared. That spectral distribution mirrors what's observed in controlled reflectors, surfaces that alter their albedo depending on viewing angle and incident radiation. So researchers asked, could there be a reflective panel underneath a translucent layer? Could the surface be opening or shifting temporarily? Some speculated phase-shifting minerals, others suspected micrometeorite impacts, but neither could account for the repetition. Not in the same quadrant, not with that precision. There is only one domain where light behavior is engineered, signaling. It's too early to claim this as communication, but the pattern, timed, repeated and clean, has made several institutions quietly assign Atlas a non-random emission classification. Because natural systems may be beautiful, but they don't repeat like this unless something is guiding them. Rotation is one of the first things astronomers measure. It tells us how mass is distributed, how sunlight affects the body, and how internal composition might evolve over time. For comets, spin is chaotic. It speeds up due to outgassing, then wobbles, then stabilizes or fragments. But 3i Atlas has broken that trend. At first, it spun at a stable rate, about once every 11 hours. Then, unexpectedly, it slowed. Not from external pressure, from something else. The object began to drift in rotation by several minutes per cycle. Then it stabilized again, then it sped up. These aren't massive changes, but they are deliberate, and they happen in phases. The spin rate curve mimics what you'd see in controlled momentum redistribution, like internal components shifting mass slightly to adjust angular velocity. The usual explanation, outgassing torque, was ruled out early. Atlas displays no major jets, and certainly no mass shedding in synchronization with its rotational changes. So what's causing the shift? Some researchers believe there could be liquid layers inside, metal-rich flows that migrate with solar input. Others suggest the core may not be frozen at all, but an alloy with variable density zones. But none of those ideas explain the rotational correction. The truth is, only spacecrafts, human or otherwise, perform such fine angular changes. Only engineered systems correct spin using internal mass redistribution. This doesn't confirm the object is artificial, but it confirms one thing. Its rotation is being managed, and natural comets don't manage anything. When JWST first focused its full spectral array on 3i Atlas, the goal was simple: identify molecules, ice, methane, ammonia, carbon dioxide, the usual suspects. What it found instead was structure. Within the mid-infrared bands, where carbon-based molecules vibrate, researchers identified repeating absorption troughs, and not just any repetition, they appeared in perfect multiples of each other. This kind of pattern doesn't occur naturally in ice. It doesn't occur in dust. It only appears in organized molecular chains like synthetic polymers, specifically chains with alternating carbon and heteroatoms, what on Earth we call engineered backbones, plastics, advanced organics, or biologically constructed frameworks. Now, to be clear, no one is saying this is plastic. What they are saying is this: these repeating spectral signals point to a material that absorbs and emits energy like an engineered chain. Even more intriguing, some of the molecular ratios matched metabolic precursors, molecules that organisms use to store or transmit energy. On Earth, we see similar patterns in ATP cycles, protein folding, and cell membrane responses. The conclusion? Whatever is inside 3i Atlas isn't just carbon, it's organized carbon. And organized carbon doesn't last in deep space unless it has protection, or a purpose. Some are calling it a fluke, others are calling it the first chemical fingerprint of something not from here. Either way, it shouldn't be there. In comet science, jet direction is one of the most predictable features. When solar heat reaches subsurface ice, the ice vaporizes. That vapor escapes through fractures or pores, creating jets that always point away from the sun, driven by thermal pressure and solar wind. But 3i Atlas didn't follow the rule. Multiple images from both JWST and ground-based observatories show faint plumes ejecting sideways. One even appeared to angle slightly sunward. At first, observers assumed the images were distorted. After all, amateur telescopes can suffer from lens glare, and long exposures can warp vector lines. But when 3 separate observatories, on 3 different continents, reported similar off-axis jets, the pattern could no longer be dismissed. If these jets were truly ejecta, they violated Newtonian dynamics. No natural material escapes into sunlight, not against the source of its own heating, so scientists turned to alternate explanations. Could these be magnetic field interactions? No, Atlas shows no detectable magnetosphere. Could these be dust trails kicked up by a collision? No, there's no sign of secondary fragments and no widening of the jet cones. That left only one plausible idea. The jets aren't random. If the object has internal heat channels, like those inferred from earlier thermal scans, it may also have controlled venting points, places where material or energy is released along predefined paths. That pattern would make it look maneuvered. Researchers hesitate to call it propulsion, but when gas leaves an object in a direction that counters solar forces and does so repeatedly, it cannot be natural outgassing. It must be regulated, and regulated emission is a form of control. Atlas may still be a comet, an ancient wanderer frozen and forgotten, but if the data holds, if the thermal grids, internal cavities, reflective pulses and rotational corrections continue, then we're no longer looking at nature, we're looking at intention, and intention changes everything. For now, the scientific world remains cautious, but curiosity is growing, and silence, especially in moments like this, is rarely without meaning. Whatever 3i Atlas turns out to be, one truth is clear: it is not like anything we've seen before, and we may not be ready for what it brings next.